Throughout the last couple of lessons, I've been alluding to the fact that gases don't actually act in this ideal behavior that we've been assuming, and instead we call them real gases. So we're going to look at that in this lesson to understand why gases don't actually act ideally. And we're also going to look at situations in which we can enable real gases to act almost as if they were ideal gases. So what conditions would be required for them to act practically ideally? So ideal gases follow the kinetic molecular theory. The first postulate of the kinetic molecular theory that they follow and that real gases deviate from is the fact that molecules occupy no space. Now, molecules do actually occupy space. They have a specific volume, and that's why gases act as real gases and not ideal gases. The second part of the kinetic molecular theory that's going to be broken by real gases is the fact or the statement that there are no attractions between molecules. There are actually attractions between molecules, and therefore that causes real gases to act differently from ideal gases. So let's understand quickly situations in which real gases can act almost like ideal gases and understand the situations in which gases act ideally. Molecules of an ideal gas are in constant motion, and they are spread extremely far apart from one another. So if gases want to act ideally, in order to simulate this being extremely spread apart, and therefore having no volume and having no attraction between molecules, gases need to have high temperature and low pressure. So let's actually look at a graph that helps us to understand this. So this graph helps us to understand why gases act the most ideally under low pressures. If you notice right here, you've got pressure on your x-axis and you've got P times V over RT on your y-axis. Well, if you remember the ideal gas equation from the previous lesson, that just equals the number of moles. So if I put 1 mole into this and then I alter the pressure and allow the other variables to change, if I have an ideal gas and PV equals nRT, then this value should stay as 1. But as you can see in this graph, it does not. At the very beginning, at very low pressures, so you can see at 0, 1 atmospheres, right there, right at 1 atmospheres, they start to deviate from the 1 mole value. And once they start to deviate, they are no longer acting ideally. And so you can see how much these gases deviate from the ideal gas, which would be just to stay at that 1 mole line. But what you should notice, the most important thing for you to notice, is the fact that at or right before 1 atmospheres, all of these gases are acting ideally. They have a value of 1. After 1 atmosphere, that's when they start to deviate, and as pressure continues to increase, then that deviation is maximized. So the lower the pressure, the more ideally gases act. The second characteristic that I talked about was high temperature. If you look at this graph right here, again, you're wanting to stay at that 1 mole line. The line, the green, red, and blue line of those 3 lines, the blue line, which represents a substance at 1,000 Kelvin, that deviates the least from that 1 mole line. And therefore that tells us that the higher the temperature, the more ideally a gas acts. And the reason why this is the case is we are wanting to minimize the attraction between molecules, which can be accomplished by minimizing pressure and maximizing the speed, the average kinetic energy that these molecules move at, therefore minimizing the amount of interactions that they have with one another, and also minimizing the volume or the space that they take up. So the second thing that I need to know is that when these conditions are not met, when you don't have high temperature and when you don't have low pressure, a real gas behaves in a non-ideal manner. And as a result, we cannot use the ideal gas equation in order to predict the behavior of a real gas. It's going to lead to errors. And we'll look at what formula or what concept we can use. It's in your textbook. We're not actually going to study it, but that's the van der Waals equation, in which you're able to modify the ideal gas law in order to take into account the fact that these gases are not acting ideally. All right, so we're going to look specifically at volume and pressure and how they deviate from what we predicted with the ideal gas law. So the volume that's predicted by the ideal gas equation is going to be too low, meaning that the volume of a real gas is actually larger than that predicted by the ideal gas equation. And the reason why is that the volume that gas molecules occupy themselves is not insignificant, and therefore it takes up volume, and therefore the volume of the real gas is larger than what is predicted by an ideal gas law. The second one is pressure. The pressure predicted by the ideal gas equation is going to be too high, and the reason why is that there are actually attractions between the molecules, and these attractions actually decrease the force with which molecules are able to collide with the walls. So the actual pressure, the pressure of a real gas, is lower than that anticipated by the ideal gas law. Molecules are more likely to deviate when their intermolecular forces are stronger, and the reason why is because they're more attracted to one another, and therefore all of these issues that we brought up with regards to real gases, they are compounded, they're made even more significant the more an attraction there is. So the stronger the intermolecular force is. So what I want you to do is to complete these notes because you have actually already studied intermolecular forces. So I want you to answer the question that's asked in your notes. The last concept we're going to talk about in this video is actually completely separate from gases now. We're going to be talking about phase changes. And the reason why I brought phase changes up in this video is because it actually should be review for you. Here's a phase change right here. If you notice, if you start at point A, if you're moving from point A to point B, as you're moving across the x-axis, you're putting heat into the system. Notice if you're going from point A to point B, your temperature is increasing. When you're going from point B to point C, temperature is not changing, but you are melting. So the energy that's being put into the system is being used to melt the substance, which is being used to break the intermolecular forces that are holding the molecules so tightly together that they're solids. From C to D, you're increasing the temperature of liquid water. From D to E, you are vaporizing the substance. Notice from D to E, the temperature does not change. Instead, all the energy is being put in to further break the intermolecular attractions between the liquid molecules in order to form a gas, in which we assume there is no attraction between gas molecules. And then from E to F, you're increasing the temperature of the gas. There are a couple of terms that we're going to use when we're working with phase changes. The first one is the heat of fusion. The heat of fusion is the heat that's required to melt a substance. Notice the units for heat of fusion are kilojoules per mole. And so that heat of fusion occurs from B to C. So that's the heat that's required to melt the substance. Another term we're going to talk about is heat of vaporization. So the heat of vaporization is the heat that's needed to vaporize the substance. So to take it from a liquid to a gas, so that would be from D to E. What I want you to notice, the phase change diagram right here, the phase change diagram above tried to show this, and this graph below demonstrates it further. The heat of fusion is always less than the heat of vaporization, which is always less than the heat of sublimation. Sublimation going from a solid to a gas. If you think about this, this actually makes a lot of sense. When I'm going from a solid to a liquid, I am breaking intermolecular forces, but that attraction between molecules still exists. So not all of the intermolecular attractions are being broken, not all those bonds are being broken. Instead, you are weakening them. So if you notice in the phase change diagram above, BC, that line is much shorter than DE. DE is much longer, and the heat of vaporization is much higher than the heat of fusion, because much more energy is required to further completely break the intermolecular attractions between molecules to make sure that gases can then move much more freely than a liquid does.